Yeah. So yesterday we talked about the proof rule for proving the termination of a program, and I did not have time to do an example. So I'm going to do this example, put it on Google Drive so that you can see it. So we'll take a proof of termination for the quotient slash reminder program. Let us assume that the program is given by this int x comma y comma q comma r, and the precondition that we assume is that x is greater than or equal to 0 and y greater than 0, because this x is being divided by y. Let me call this a, and let us assume we start with the program now. R is set to x initially, x, and q is set to 0. Let me write the program and then we'll write the loop invariant. While y is less than or equal to r, please see this over here, slightly different version of the r is assigned the value of r minus y, q is q plus 1. So it's basically repeated subtraction for computing the quotient. Okay? And every time you subtract y, you add 1 to the quotient. So now, what might be the loop invariant? The loop invariant is basically something like this. R is greater than or equal to 0 and x is equal to q star y plus r. Okay, let me call this point B. Okay, and after the program is executed, we still have x is equal to q star y plus r, and we have 0 less than or equal to r, less than, strictly less than y, satisfied, because every time is subtraction y. Let me call this point C. Okay, to prove the termination, we have two paths. And what are these two paths here? Going back to this path and this path, which need to be proved. Okay, let us use E is equal to sum r plus y, which is also the value E naught that we start with. Let P be the loop invariant LM. Then we have P and B implies E greater than 0. This should be true at B. True at B. Okay, the location B in the program over here. All right. Now, and the other condition, let me call this condition 1. Another condition that must be satisfied is that the value of E naught before execution of the loop is strictly greater than the value of E than the value of E after the execution of the loop. Okay, this needs to be satisfied. So let's see this. So what do we need now? This means the termination condition from B to B loop is entered again must be satisfied. Must be true. Let's look at this. P and B implies E naught greater than E and E is greater than or equal to. Okay, of course, once the expression becomes 0, we are coming out. E naught is E before execution of loop. The termination condition at B, what is it now? Becomes R is greater than or equal to 0 and X is equal to Y star Q plus R and Y greater than 0 and Y less than or equal to R, because what we started out with. And this should imply R plus Y is greater than 0. Okay. How can you prove this? R greater than or equal to 0 and Y greater than 0. This implies R plus Y is greater than 0. This implies condition at B is true. Now let's look at the second part. Condition B to B is true. Assume X, Y, R, Q have values A, B, C, D on entering the loop. So this is going to lead to your E naught. We have, so this is basically X, this is Y, this is R, and this is Q. Clearly, on entering the loop, the loop we have C greater than or equal to 0 and A is equal to B star D plus C and D greater than 0 and B is less than or equal to C. This is what we started out with. Okay, remember, because initially R is initialized to X. Then we have, this implies C plus B is greater than C minus B plus B. Okay, which is true anyway. The C is greater than 0, B is greater than 0. So this can be shown to be true. True using the rules of arithmetic. Okay. That means what? We have now E naught is equal to C plus B before the loop execution, and E is equal to C plus B minus B. Okay. This implies E naught is greater than E after the execution of the loop. This completes the proof of termination. Proof of termination of the